It appears to be working. Thank goodness. All right, so we've been talking about general linear models, right? And that term has a very specific meaning. General refers to a choice as to what the model residuals are supposed to look like. And so I've sort of mentioned this as an aside. The last few slides here are doing a little bit deeper dive into what the actual assumptions are that underlie the use of this model, and more importantly, the use of this model to make inferences. So it's not the estimates of the fixed intercepts and fixed slopes per se that we're worried about. It's their standard errors, and the standard errors, because estimate divided by standard error is your test statistic, and then you get a p-value that goes with the test statistic. Everything related to whether or not your p-values are trustworthy has to do with whether your standard errors are trustworthy. So everything with respect to inference, it lies in the standard errors. So that's where the assumption part comes in. There are lots of ways of getting standard errors, but if you use the off-the-shelf formulas that are programmed into ProcGLM, then that process comes with it then a set of assumptions that you have to be willing to say are at least plausible for your data. So I'm on lecture 3, slide 28. Look at the show started here. So to reiterate, I've tried to make this point a few times, but I want to try and make it again because it's super important and super misunderstood. The idea that the general linear model is for normally distributed outcomes is incorrect. It's for normally distributed residuals. And so the difference is when I say outcome, I'm referring to the marginal distribution of the outcome. So just what it looks like, say, for this picture on the left, whereas the distribution on the right is for the outcome residuals. The e's for each person, how far off each person's actual y is from the y that's predicted by the model given y hat. And it's the e's that are supposed to be plausibly normal. So you can't tell just from looking at an outcome whether or not the residuals are going to be normal. If you think about an extreme case, if you had two groups that were super different from each other, like you had a control group versus a treatment group, and the treatment absolutely worked, in terms of the outcome, what kind of shape would you expect in that situation if you just made a plot of what the outcome histogram would look like? There's a word for it. If you have two groups that are clearly separated, the word starts with a B. Any guesses? No guesses? The word is bimodal. And the picture that would go with it is like two mountains, basically. Like you have two groups and they're clearly separated. If you looked at an outcome like that, you'd be like, this is bimodal. There's no way this thing's going to be normal. But once you factor in who is who in terms of group membership, then the E residuals that are left over could plausibly be normal. So this is, there's an article about this, and I'm trying to make this point here. It's the residuals that have to be normal to believe the results of the analysis, and you don't know what the residuals look like until you've done the analysis. So there are tests for whether something is normal enough. Historically, these models are fairly robust to mild deviations from non-normality. Where you have to watch out is for outcomes that are never going to have a normal residual distribution no matter what. So if your outcome is binary, if your outcome is bounded, so like if it's a binomial outcome where it can't be continuous, things like that, there are other models for those kinds of outcomes instead. So the way that this is written in terms of expressing marginal, what y looks like originally, versus conditional, meaning the leftover e part of y, is like this right here. So we say that y sub I is normally distributed, so that little squiggle tilde thing, that means distributed as. It's distributed as y hat sub I. So that's the idea of the regression line that is created by the model. That's the mean that is predicted for each observation. So anybody with the same set of predictor values would have the same conditional mean, but because it depends on your predictors, that's why it has an I here. And then the variance part of the normal distribution is sigma squared E, and that is a constant. in the normal distribution, we have one number that is supposed to be the variance that holds for all cases. And so that can go wrong in to the extent that the same amount of variance doesn't hold for all the cases. So we'll tackle each of these assumptions in turn. So there's three things that you have to be willing to believe about the E's to believe the results of the analysis. One of them is that they're normally distributed. What if they're not? Well, some textbooks would suggest that you should transform your outcome variable. So take the log or the square root or something along those lines. That only works in some cases, and it's probably not the most desirable way to approach it. There are certain kinds of variables that you cannot transform to be normal no matter what. And for those sorts of situations, your best option is to pick another model. So that's where the terms general versus generalized come in. Ized means some kind of not normal residual distribution, some kind of not normal conditional distribution. So I have a class that I created the first time last spring. It'll come back the following spring. I would recommend that as a follow-up to this class. That's what I designed it as. It picks up where the GLM leaves off, and you can learn how to do the same sorts of analyses, predicting all different kinds of outcomes. So that's generalized linear models for categorical outcomes, counts, skewed continuous variables, and things like that. The other piece of it is that the residuals are supposed to be independent. Now that's a big one. If that doesn't work, you can't trust anything. Independent means that there are no additional relationships between the E's that aren't already built into your model. So this would be violated in practice whenever you have more than one outcome from the same person, so repeated measures kinds of designs. Also when you have people who are nested in naturally occurring groups. So if you sample children from multiple schools, if you sample patients from multiple hospitals, survey respondents from multiple countries, you have to be able to build into the model the fact that people from the same group are likely to have more related residuals than people from different groups. So there are models for that, and that's my other set of classes that deal with multi-level models, or what's known as mixed effects models, in which the solution to it is to build in additional layers of E residual terms that in turn predict a correlation between the responses from the same group. So that is an important thing to be aware of when we're doing these analyses. If you're in that situation where your research concerns people from groups that matter, like you didn't assign them that way, they just came that way, then the GLM is probably never going to be the right choice. So do any of you have research that you're thinking of that you want to be involved in, are involved in, that would fall under that category? Doesn't come to mind? Yeah. Go ahead.
Can you explain again when you're talking, like, so groups that you didn't put together but they were naturally together? That's what you're talking about?
Mm-hmm.
So it wouldn't necessarily be like a group that shares a similar identity. Would that be one if they're, I guess I'm trying to think of like research that I might be interested in that would require like particular like identity traits, but that wouldn't necessarily be the same because I'd be creating that group. Does that make sense?
Yeah, can you give me an example about what kind
Yeah,
of
so
identity?
let's say I wanted to like study like Latinx undergraduate students. Is that what you mean, or it's more like if it were perhaps like Latinx students who came from a particular area?
Mm-hmm.
Is that more what you mean? Or maybe I'm off totally.
No,
I'm more
you're
asking.
on.
Okay, okay.
Yeah, that's not an expression, but no, you're on. You're on totally. So yeah, that's actually a great example. So if you wanted to think about, say, experiences of Latinx students versus experiences of people who do not have Latinx heritage or don't identify that way, right? Like a simplistic way of looking at that is, yeah, you've got two groups, and once you put in the model who's who, you're good, right? Except that even I know enough about Latinx to know that that refers to a whole bunch of different cultures from a whole bunch of different places, and it's not one thing. And so that's a great example of when you'd have to worry about this, because you would have individuals from particular subcultures or who have particular heritages, or however you want to phrase it, would be more alike even after you control for the fact that they identify as Latinx. So it's any time that you would have that the grouping in your data is not accounted for by the predictor variables. So as another example, treatment versus control might be a manipulated condition. But if you're doing school research, you may have, say, 10 treatment schools and 10 control schools. Well, then the kids who are from the same school, even after you control for whether it's a treatment or control school, are probably going to be more related, because not all treatment schools are equal and not all control schools are equal. So that's when you'd have to worry about that as well. Alex with his cat, your N of 1 designs, right? Like if you wanted to have, say, 4 N of 1 designs simultaneously, then you'd have to put into the model, in order to pool the data, terms that would distinguish the observations from each of your single cases, because then they're like a group that you would have to worry about. So this is the big one to watch out for, because basically none of the standard errors will be right if you have this kind of, it's called dependency, which means correlated residuals in your data. So that's the big one. Another one that is actually related to the assumption of normality more so is an idea of constant variance. And I didn't make up these terms, so don't shoot the messenger, but the idea for constant variance is a term called homoscedasticity. That's a hell of a Scrabble world, right? And if you don't have constant variance, the term for different variances is heteroscedasticity. I like constant variance better. But the idea of this is that the model works equally well for all your cases. Like that's the basic idea of this. So I have a picture here that I stole that I like this, that conveys this idea. We have a regression line. So X is on this axis here and Y is over here. And what the model is saying is that the way that the points fall off of the line, they do so in an even manner all along the line. So there's a normal distribution for the points that would happen at each point of the regression line. Where that might break down is something like this picture down here, which I stole completely because I loved the way they wrote the labels. Good? Not good. It doesn't get much clearer than that. So why it's good is that the points are equally dispersed around the line. It's flat and it's even. So there's no point on the line at which the line stops working as well. In contrast with the not good picture, this fanning shape as it's called, what this implies is that the line works less well the further up you go on X, that there's more unexplained variability amongst the high X cases than the low X cases. And this can happen anytime that you have an outcome variable with a lower boundary. So in counts, for instance. Like if you have somebody with a count of 1 and you predict a count of 0, like you can't, there's no room to be off by very much. But if you have somebody with a count of 50 and the model predicts 40, like there's a lot more variability in counts that are possible as you go up the ladder. So this kind of non-constant variance and non-normality tend to get tackled with the same strategy of generalized linear models. But for continuous outcomes that actually do look normal that have these problems, you can actually build a term into the model for the variance, as it's called, that allows the ease and the variance of the ease to depend on a predictor. So you can't do that with ordinary least squares estimation, but you can do that with maximum likelihood best estimation. So that's not something that we'll have a chance to talk about this semester, but I can give you some resources if you're interested in learning more about that. So the point of the story, I think this is it. Yeah, almost it. The point of the story is that if the data that you have don't fit the assumptions of the model, you don't fix the data, you find a new model. And that's the thing that I want you to remember out of all of this, is that there is a solution for it that people smarter than me have already came up with. And you don't have to be like, well, I guess I can't do my analysis then because my stuff's not normal. Guess what? Normal distributed variables are very rare. in real life. I know they say that that's everywhere, but not so much the ones that we collect in social sciences. So normality, constant, variance, and independence, those are all things that you can choose a different model that has a different set of assumptions with it if you're in that situation. In the example data that we had, so we were predicting income from education and from marital status in example 3, and you'll get a chance to practice these sorts of models in homework 3. The one on the right here, the distribution around the predicted income for people who are unmarried versus married, these, I tried to highlight it here in purple. The width of this looks about the same for both groups. So it looks like the variance of the E residuals is fairly similar, just eyeballing it within the 0 group and within the 1 group. But over here for income, we have the same problem that was on the not good slide on slide 30. We have this fanning effect, where the model does less well at predicting income amongst higher educated people. And there's a lot more variability on this side in what income could be, and part of that is due to the fact that income is bounded at 0. So there's less room to be wrong on the left side of the picture here. So, all right, how are we doing? Questions or comments about how this applies in your lives? The good news is that even if you find yourself needing a different kind of model, absolutely everything that we've talked about this semester generalizes to that case. You just have to add on additional layers of things you haven't learned yet to what you know now. But this idea of linear models as a core will stay with you, and it works throughout statistics in terms of how you would build models to predict things. So then, wrapping things up, general linear models is what we're going to spend the rest of our time on this semester. We have general is for normally distributed residuals, generalized is for anything else. So far we've talked about only 2 different models. An empty model as a baseline, so with no predictors, it looks like this. If you don't know anything else about a person, your best guess for their outcome is just going to be the grand mean of the outcome variable, so that's what beta 0 becomes in that model. Once we add a predictor, then your best guess for a person's outcome is a function of 2 things. A reference point for the model as the intercept, which is the expected outcome value when the predictors are 0, plus a linear effect at this point of a predictor centered such that 0 is meaningful. So in terms of talking about the effect on the residuals, note that the empty model is nested within this one. The term nested means that one is a subset of the other. So the thing that makes the empty model different from the predictor model is the addition of beta 1. The idea that we had a fixed intercept in both, but now we're picking up the effect of beta 1 to describe how x relates to y. So that means that any difference in the E residuals and their variance, cough cough homework question, has to be due to the new thing that distinguishes these models, the beta 1. So E as a concept in the empty model represents all of the variance in the outcome that is to be had. After we then include a predictor, that E variance should go down to the extent that that predictor matters in terms of relating to the outcome. And everything you learned about correlations in terms of how you talk about these relationships still holds. The difference is that these are unstandardized units. So if beta 1 is a slope, it's positive. That means as x goes up, y goes up, and it goes up by the units of the variable. So beta 1 is the difference in y for a 1 unit difference in x. So to know what to do with that number, we have to know what the units are. Beta 0 is always the same thing in terms of an intercept. It's the expected outcome when your predictors are 0, and the residual is always how far off you are. So we keep track of these deviations, these residual offnesses, and ideally we watch their variance shrink as you add more predictors to the model. And in terms of an effect size, up to this point, everything that we've done is the same thing as Pearson correlation. It's either a linear relationship between 2 quantitative variables or a relationship between a binary with a quantitative outcome. So all of this is not new in terms of what it's telling you, but it is new in how we can extend it to do more complex things. So this is the foreshadowing of what's left this semester. We've hit the halfway point, right? This would have been spring break. Woo, I know. Let the countdown begin, right? You've made it this far and you're still alive to tell about it. So where we're headed then, why would we bother to do the same thing that Pearson's correlation gives us? It's to be able to extend it to do different things. So what we're going to talk about next then is extending the kinds of categorical predictors that can be included. So we're starting off with a 3-group variable, and you'll get a chance to practice a 4-group variable as a predictor in your next homework, homework 4. We're also going to be talking about how to specify nonlinear effects of quantitative predictors. So curvilinear effects, effects that change directions, effects that level off, effects that are piecewise or linear splines as they're known. So different ways of talking about how a quantitative variable relates to an outcome. Lecture 5 and example 5 then is adding multiple predictors at the same time. So what is known colloquially as multiple linear regression, where the goal is to see to what extent each predictor contributes uniquely after controlling for what they have in common. And then wrapping up the end of the semester is going to examine models for moderation. The idea of moderation is that the effect of a predictor depends on your level of another predictor. So that is examined using interaction terms, which can be a very tricky thing, but they're very common, especially in the models that I teach in my other classes. And so I want you to get some practice with those, and that will be your last homework based on that as an idea. So how's that sound? I'm hoping that even those of you who've had these classes before, that we start hitting on some new stuff that you haven't seen yet. So feel good? Maybe? You're all looking very subdued here. We're good? Getting sleepy? Maybe? Should I take it personally or no? No.
I think I'm generally like, it's making sense. I'm just trying to make sure it's making sense enough that when I go back to the homework, I know how to like apply what you're saying to like new numbers and things like that. So that's where my face is.
It's the concentration phase.
Yeah, that's it.
Yes, I understand that. I used to have people complain about me when on like customer service cards at the restaurants I worked at as a waitress, because they would see me like with this like face that looked like I was angry walking around the restaurant. No, I was concentrating. I was like, I need water, table 2 needs bread, I need to get an extra sauce, table 4 needs their check. Like, that's my face, right? So I understand. I'm trying to stay with y'all, because I never want to be that person who just keeps talking when no one is listening. Right? I've been in those classes, and that is an awful experience that I try not to repeat. All right, so we're done with this one then. So any questions before we start the next topic? More complex general linear models. No? We're ready for it? Ready enough? Okay. Lecture 4 then. On to some new stuff.